let's continue. So today I consider solution of initial value problem for the wave equation in the plane in 2 dimensions. So it is wave equation in 2D. It's interesting that first we considered solved the equation in 3-dimensional space, and after that in 2-dimensional space. Why not in opposite? It would be quite natural. We started from n equal 1, which is string equation, and then it would be next step n equal 2, and then next step n equal 3. Logically and historically, 3-dimensional equation in 3-dimensional space is simpler because the problem how to find the radial solution, which depends only on model x and on t, it reduces to just a string equation. Yes, and then we found easily solution of this equation, and then fundamental solution, and in the whole space it's enough to find the full solution of initial value problem. In 2 dimensions, this does not work, because in 2 dimensions, if you write the equation for radial solutions, it does not reduce to the string equation. So we have to do some trick. So this is the trick which was invented by the great mathematician Jacques Adamar, from 3 dimensions to 2. So our problem is the following: Laplacian utt minus Laplacian xu equal 0. Here u equals u of xt, x in R2. And the initial condition, u for t equals 0 equal f, ut for t equals 0 equals g. So this is our initial value problem. First of all, let us return to 3-dimensional equation. Consider equation utt minus Laplacian u equals 0. U equals u of x1, x2, x3, t. So it is a full 3-dimensional equation. But now consider the solution which depends only on x1 and x2, and they don't depend on x3. So consider only solutions. U of x1, x2, t, which don't depend on x3. So these solutions are in 3 dimensions, but they depend only on x1, x2. So these solutions look like this. So it is x1, x2, x3. So solution at every t depend on x1, x2, and x3. But if you draw the line, vertical line, parallel to x3 equals 0, going through the point x1, x2, say 0. So u of x1, x2, x3 equal u x1, x2, 0. Yes, so it depends, essentially it depends only on x1 and x2 and x3. So it looks like such a cylindrical function. So it's it is surfaces where this function is constant are cylindrical surfaces. You have to draw the surface u of x1, x2 equals constant, yes, then it will be a cylindrical surface. So therefore we consider just the functions which depend only on x1 and x2, but we apply our machinery of solution of three-dimensional problem. Yes. So consider the following thing: u ct minus Laplacian u, Laplacian u x1 x1 plus u x2 x2 plus u x3 x3 equals 0. So we solve this equation, but initial condition u at t equals 0 equals f of x1 x2. Again, such a cylindrical function. It does not depend on x3. Ut for t equals 0 equals g of x1 x2. Yeah. So it is a three-dimensional wave equation, but with initial conditions which depends only on x1 and x2. And we are looking for solution which depends only on x1 and x2. So u x1 x2 t. But to find this solution, we use three-dimensional formulas, this same Kirchhoff formula. And consider first the particular case when f is 0. So u tt minus u minus Laplacian u equals 0, u for t equals 0 equals 0, ut for t equals 0 equals g of x1 and x2. Yeah. So again, this is a full three-dimensional equation. Yes, but the initial condition is one is 0 and other is this degenerated function which depends only on x1 and x2, though it is in three-dimensional space. Yes. Then solution is given by the same formula, Kirchhoff formula, which I wrote last time. U of x t equals 1 over 4 pi t, integral of y in s in x and radius t, g of y dsy. Yes, so if you take here some point x1, x2, x3, t, yes, then solution is obtained from the initial condition, initial function g, by integrating over the sphere s of x and t, radius t. Yes? And now just look, if you shift this sphere to other position along the x3 axis, so it is the point x1, x2, x3 prime, t. x3 prime is different value of x3. No, not t. Yes, and this is the sphere of radius r, s of x prime t equals x prime equals x. Yes? So if you shift it along this vertical line, then the function on this sphere will not change because the function is invariant under these shifts. Yeah? So solution will be at this point for time t will be the same as solution at this point. Yes? So the result will be again a function which depends only on x1 and x2 and t, and does not depend on x3. So we have this formula, and it is tempting to take g of x1, x2 equals delta of x. 1 x2. Yes, so it is delta function in the plane concentrated at 0. So it is a function which is 0 everywhere, and integral of this function is 1, so it is just point mass. Now, maybe it is too severe to start from this. Let us take, so better take g of x1, x2 equals phi epsilon of x1, x2. Yeah, so it is a function which is concentrated in disk of radius epsilon in the plane around the origin in the, it is x1, x2 axis. So the function concentrated in this disk such that its integral is 1. Yes? And so let us evaluate the integral of this function over the sphere. So there is x1, x2, x3. So the function phi epsilon of x1, x2 in this three-dimensional space, if we add variable x3, and the function depends only on x1, x2, so the function is concentrated in the cylinder of radius epsilon around the x3 axis. So all the function is here. Now we take the point, any point, say, because the result will not depend on x3, as I told. So we can take this point on the axis, say x1 here. Yes, and then we draw. Let us draw the. Let us draw the sphere around this point. It is the point x. Let me draw it somewhere here in the x1, x2 plane, but maybe not on the axis, but the radial, the distance is, say, r. The distance r from x equals x1, x2. The distance r from the x3 axis. Then if t is less than r, then the sphere will be too small and it will not reach this cylinder where the function is not zero. So the integral will be 0, it is t. Integral over this sphere will be 0 if t is less than r. So here it is 0. No, r minus epsilon, but epsilon is small, so let us a little bit neglect it. So it is r. And then it will, for t more than r, it will have some intersection with the cylinder. It intersects this cylinder along these two pieces. It is upper intersection and this is lower intersection. Yes? And we have to integrate this function on this sphere. Yes, so how to evaluate this? No, let me do some construction. I take a plane which contains the point x and the z-axis, and let us draw in this plane. Okay. If necessary, I will repeat this formula. So this is the section of this sphere of radius t. Radius is t. This is the distance r, and our function is concentrated in this small strip. The small cylinder like this. And these are the intersections of this cylinder with our sphere. How to evaluate it? So if it is this point does not lie, point x does not lie on the axis of this cylinder. If it lies on the axis, then we will have this picture, and so this intersection has the area equal to area of cross section of our cylinder. Here it is a little bit inclined, And so the area increases. So how to evaluate with this area? So let us do this simple geometrical construction. Consider this triangle. Let me remove this. Consider this triangle, say it is point O, it is point X, and this is point A. Yes, this is right angle, and the area of this, let us call area of this small piece area of this small piece, how to say it, say ds. Yes? Area of ds equals area here of dx, this is dx, times divided by one moment. So this have angle phi, sine phi. Yes? Or cosine psi equals area of dx divided by cosine psi. No, it is the same. So, we have triangle. It is R, this is T, and this is square root of T square minus R square. And phi, sine phi equals square root T square minus R square divided by T. Yes, this divided by this. And we have to divide by sine. So area of ds in this cross section equals area of dx, its projection on the horizontal plane, divided by sine phi equals area of dx divided by square root of t square minus r square multiplied by t. Now, we have to integrate the function, this function phi epsilon, over this domain and over this domain. So, integral over s of x t phi epsilon of x 1 x2 ds x dsy okay, of y1 y2. X is here and y is here on the sphere. dsy equals 2, because we have to take into account this, integral integral over R2 phi epsilon over y1 y2 dsy it is dx times t divided by square root t divided by square root t square minus r square dx dy 1 dy2. Yes, but integral this is a constant, and this is integral of phi epsilon is 1 over dy1 dy2. So this means that it is equals 2t divided by square root t square minus r square. Yes. Now up to small corrections because it is a little bit curved, so this here this angle a little bit changes. Now we have to take epsilon going to 0. So and this with just a limit of this expression. Okay, so we have this result, and now let us substitute it into the formula. U of x1 x2 t equals u of xt equals x1 x2 0 t and t because we are in three-dimensional case, but the point stays say on the plane x1 x2. Yes, equals 1 over 4 pi t times 2t divided by square root t square minus r square equals 1 over 2 pi square root t square minus r square. Where r square equals x1 square plus x2 square. And as I said several times, this solution does not depend on x3. Yes, it is invariant under shifts in the x3 direction. So this is solution of two-dimensional Laplace equation with initial value g is delta function. Yes. So again, this solution. Let us denote this solution. No, okay. U of x1, x2 t equals 1 over 2 pi square root t square minus x1 square minus x2 square. Yeah? And now we can forget about the third dimension, the third coordinate, because it does not depend on the x3. But if you consider a graph of this as a function of r, so how it behaves for t equal for x1 for r equals 0 equal 1 or 2 pi square root t square minus r square. So for r is 0, it is 1 over 2 pi t. One over 2 pi t. And then it grows because the denominator decreases when r grows, yes, and then at r equal t, the denominator becomes 0, so it goes to infinity, but it is not such a strong singularity because it is just like 1 over square root, so it is integrable. This function is integrable. And what happens if r more than t? It corresponds to the case when this sphere did not reach the axis, x3 axis. And so in this case, the integral will be honestly 0. So here it is 0. Yes. Now, to check it, this solution, let us find the integral of this solution, integral of this function. What we should expect? How can we physically interpret this solution? It's interpreted as follows. We have a sort of membrane, yes, two-dimensional membrane, and we gave at time 0 a kick at one point with unit impulse. Yes, so it is delta-like force given to the membrane. So it is two-dimensional membrane. And this is 0, and at time 0 we gave here an impulse such that this impulse was delta-like in x and in t. So integral of this delta-like force is 1, but the fall, the force is 0 for t different from 0. Yes, so if you consider just a body and the force which acts on the body is delta function of time, this means that at time 0 we gave this body a unit momentum. Yes, because momentum is integral of force over time. So if the force is delta function, then this integral is 1. And then the body is set into motion, and its displacement is proportional to time. Yes? Here the same, but here the membrane is not moving like a solid body. It is different parts of this membrane are moving with different speeds. Yes, which we are studying now, this motion of membrane. So this means that the integral of this function, it is so to say total displacement of membrane, should be proportional to time. So let us check that it is the case here. So integral u of xt dx, x in R2, equals integral over R2 dx divided 2 pi square root t square minus r square equals, no, it is a function depending on t. For any t depends only on r, so we use the polar coordinate. It is integral 2 pi rho d rho, integral from 0 to t. Yes, because after t it is 0. 2 pi rho d rho divided by 2 pi square root t square minus r square equals integral from 0 to t rho d rho square root t square minus rho square Now we say rho square equals s, d s equals to rho d rho. Yes, so it is equal integral ds divided by 2 square root of t square minus s, integral from 0 to t square. So this function for if it is 0, if s is 0, equals t square. Here, if it is t square, it is 0, so equals integral from 0 to t square ds 2 square root of s equals square root of s from 0 to t square equals t. Okay? Now you can repeat this calculation yourself. So this means that in fact the transmitted momentum is equal 1 after this impulse, and then what we see that after the result will be the circular wave, which is propagating in all directions, and if you consider the profile of this wave, it will be like this. This profile. That's it. So this means that we found this function, our function u, and let me denote this function somehow. And I denote this function g of x t equals 1 over 2 pi square root t square minus module x square. And then we can write the solution of our initial value problem. So utt minus Laplacian u equal 0, u equals u of x1, x2, t. So it is in two-dimensional case. U for t equals 0 equals 0. Ut for t equals 0 equals g of x. Yes? So we have this problem. And similarly like we did in the previous case, so this G is a reaction of this membrane if you give a kick at one point, at the point 0. If you give it a kick having some profile G of x, so it is a distributed function. Yes? Then we have the u of xt equals integral y in R2, g of x minus yt, g small of t of y dy. And this formula is works in any dimension. Simply g is different. G is different function depending on dimension. Now to go further, how to solve the full problem. Utt minus delta u equals 0, u for t equals 0 equals f, ut for t equals 0 equals g. Yes, this full initial value problem. So we started from some configuration of our membrane. Yes, it's level line, something like this. And we also gave initial velocity, vertical velocity at every point, like in case of a string. Then you have the same formula as it was in case of string and in case of three-dimensional wave equation. So u of xt equals integral over R2 g of x minus yt, g small of y dy plus d dt of integral over R2, the same function g x minus yt, f of y dy. Yes? Because it is what is in the bracket, it is solution of the problem where here is f instead of g. So we have, and if you differentiate it, then we have also a function satisfying the wave equation, but in this case it's if you differentiate, this means that at the initial moment you have the value of derivative is what was previously is f. Yes, but if you differentiate it, then it becomes the value of derivative. Yeah, the value of this okay, so if you consider this integral, then this function will be 0 at initial moment. It is derivative, it equals to f. And if you and this function satisfies the wave equation. If you differentiate it for time, the derivative will have value f at initial moment, and the second derivative will be 0 because second derivative is at initial moment is just the Laplacian, because all in all it satisfies the Laplacian equation, wave equation. So if initial function is 0, then its Laplacian is 0, so the second derivative is also 0. The second derivative of this function in the bracket is the same as the first derivative of this function. So this means that this term satisfies the problem where this is 0 instead of g. This term solves this equation, this problem, and all in all they solve our full problem. So everything depends on this function g. And now to finish, let me list again this function g, how they look in the dimension 1, 2, and 3. So g, it is the same letter as I used to define to denote the Green's function for the Laplace equation, and it plays a similar role. I will hope to show you next time. So Green's function for the wave equation in dimensions 1, 2, 3. So we have a Green function g of x t equals g of module x t equals g of rt. So it depends only on the distance from the origin in the space and of time. N equal 1. G of rt equals 1/2 if r less than t, 0 r more than t. No, okay, like this. Clear? N equal 2. G of rt equals 1 over 2 pi square root t square minus r square, r less or equal than t, 0, r more than t. N equals 3. G of rt equals 1 over 4 pi t delta function of r minus t. Because delta function, because we integrated over the sphere, and anyway we got this first, this delta, and then interpreted as integration over the sphere. So let me draw the picture. n equal 1. It is 1/2. It is t, and here it is 0. So we have this. N equal 2. It is t. It has this singularity, but not very strong, but it goes to infinity, but like square root. And here it is again 0. Yeah? It is n equal 2. N equal 3. Equals t. Here it is 0. Here it is 0. And here it is delta function. No, let me draw it this way. So we see that the higher dimensions of this space, the more singular becomes this Green's function. Yes? They have one common feature that for t, for r more than t, it is 0. But this is constant for r less than t. This is some function which has singularity but not constant and not 0. This is 0. And here we have a concentration of all this function at the point t. That's it. We can say some more things about this, but let me do it in the next lecture. I don't want to overburden it. You know, there is a good principle which I am not true to this principle, that lecture should contain just one idea. No, I hope to be close to it in this lecture. This idea was not mine, but nonetheless I love it very much. So let us finish. Have a good time. Bye.